the box that contains a ghost and a mouse at the same time. Let's begin in the quiet stillness of an ordinary room. Imagine it dimly lit, with only the soft glow of a single lamp casting long shadows across the floor. In the center of this room sits a small wooden box, unassuming at first glance. It is closed, sealed tightly, and silent. But inside lies something extraordinary, or rather, two things at once: a ghost and a mouse. Not one or the other. Both. Now, you might smile at that idea. Ghosts and mice don't typically share space, and yet there is something deeply unsettling about the image. If you were to open the box, you'd expect to find either a ghost or a mouse. Not both, because that's how reality works, right? Things exist in one state or another, alive or dead, present or absent, either or. But what if they didn't? What if, before opening the box, both possibilities coexisted, not just in your imagination, but in actuality? What if the ghost and the mouse weren't figments of fantasy, but metaphors for something far stranger, something rooted in the fabric of the universe itself? This is the essence of Schrödinger's cat, a thought experiment devised nearly a century ago by Austrian physicist Erwin Schrödinger. At its heart lies a paradox so bizarre it has haunted the minds of scientists, philosophers, and dreamers ever since. It is not merely a riddle about a cat in a box. It is a window into the strange world of quantum mechanics, where the rules of classical physics no longer apply, and where objects can be in multiple states at once, suspended between existence and non-existence, until someone looks to understand why Schrödinger crafted this peculiar scenario. We must step back into the early 20th century, a time when the very foundations of physics were being shaken. Classical physics, which had reigned supreme since Newton's day, was built on certainty. Objects moved along predictable paths. Causes led to effects. Reality was solid, measurable, and independent of observation. But as scientists delved deeper into the microscopic world of atoms and particles, they discovered something profoundly unsettling. The subatomic realm did not obey these familiar laws. Instead, particles behaved more like waves of probability, existing in a haze of potential outcomes. They could be in multiple places at once. They could pass through barriers they shouldn't be able to, and most disturbingly, their properties seemed to be undefined until measured. This new framework, known as quantum mechanics, gave rise to what is called the Copenhagen interpretation, primarily developed by Niels Bohr and Werner Heisenberg. According to this interpretation, a quantum system does not settle into a definite state until it is observed. Before that moment, it exists. In a superposition, a blending of all possible outcomes, each with a certain probability. It was this idea that Schrödinger found deeply troubling. To illustrate the absurdity he perceived, he proposed his infamous thought experiment involving a cat. Let us walk through it again, slowly, deliberately. Inside the sealed box is a cat, a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The radioactive atom has a 50% chance of decaying within a given time period. If it does decay, the Geiger counter detects it and triggers the hammer to smash the vial, releasing the poison and killing the cat. If it doesn't decay, nothing happens, and the cat remains alive. From the perspective of someone outside the box, the atom's decay is a probabilistic event governed by quantum mechanics, until the box is opened and an observation is made. The atom exists in a superposition of both decayed and not decayed. Consequently, the entire system, including the cat, must also be in a superposition of both alive and dead. This is the crux of the paradox, the idea that a macroscopic object like a cat could be simultaneously alive and dead simply because no one has looked. It challenges our deepest intuitions about reality. We know cats are either alive or dead. We don't see them flickering between states like some cosmic illusion. And yet, according to quantum theory, that is exactly what should happen, unless something about the theory itself is wrong or incomplete. Schrödinger himself did not believe the cat was literally both alive and dead. He created the thought experiment to expose what he saw as a flaw in the Copenhagen interpretation, that it led to nonsensical conclusions when applied to everyday objects. If quantum mechanics says the cat is in a superposition, then surely there must be something missing from the theory. Or perhaps, as some later interpretations suggest, the act of measurement itself plays a special role, even a conscious observer. That brings us to one of the most profound questions raised by Schrödinger's cat. Does observation create reality? At first glance, this seems like a philosophical musing. But in the world of quantum mechanics, it's a scientific question with real implications. Some interpretations of quantum theory suggest that until a measurement is made, the system remains in a kind of limbo, a cloud of probabilities without a definite outcome. Only when someone observes the system does it collapse into one particular state. This raises an unsettling possibility that reality is not objective, but dependent on the presence of an observer. Without someone to look, the universe might remain in a state of infinite potential, like the cat forever balanced between life and death. But who or what qualifies as an observer? Is it a human consciousness? Could a machine count as an observer? What about a passing photon? These are not trivial questions. They strike at the heart of what it means to be real. Some physicists argue that the collapse of the wave function, the process by which a quantum system settles into a definite state, doesn't require consciousness at all. Decoherence theory suggests that interactions with the environment cause the apparent collapse, meaning that even without a sentient observer, the cat would end up definitively alive or dead due to countless tiny interactions with air molecules, thermal vibrations, and electromagnetic fields. Others, however, cling to the idea that consciousness plays a unique role in the universe. This view, sometimes called the von Neumann-Wigner interpretation, posits that mind and matter are fundamentally connected, that it takes awareness to bring reality into focus. While this idea is controversial and lacks experimental support, it continues to inspire speculation and wonder beyond the scientific debate. Schrödinger's cat also invites us to reflect on the nature of uncertainty itself. How much of our lives are spent waiting for outcomes to resolve? How often do we feel caught between possibilities, unsure whether to move forward or retreat, to speak or stay silent, to hope or surrender? The cat in the box becomes a metaphor for our own existential condition. We live in a world of unknowns, constantly teetering between what is and what might be, and like the cat, we are shaped by the act of observation, by the moments when decisions are made, doors are opened, and possibilities collapse into reality. As we sit here, contemplating this strange little box, let us pause for a moment. Take a slow breath. Let your thoughts drift. Imagine yourself standing beside the box, hand hovering above the lid. You know that when you finally open it, the mystery will dissolve. One truth will emerge, alive or dead, ghost or mouse, clarity or loss. But until then, everything is. still possible, and now, as we close the lid gently and step away, we prepare to journey deeper into the mysteries of the quantum world. In the next segment, we will explore a principle so subtle it governs everything from light to life itself. A principle that tells us the universe is not only stranger than we suppose, but stranger than we can suppose. Until then, rest easy. Let your mind wander through the corridors of possibility, and allow the gentle rhythm of this night to carry you further into the unknown. The uncertainty principle, when not knowing, is fundamental. There is a quiet elegance to the idea that some things are simply unknowable, not because we lack tools or intelligence, but because the universe itself does not permit it. This is the heart of Heisenberg's uncertainty principle, a cornerstone of quantum mechanics and one of the most profound revelations about the nature of reality. It tells us that uncertainty is not just a limitation of human knowledge. It is built into the very structure of existence. To understand this principle, let us begin with something familiar: motion. Imagine watching a bird in flight. Its wings beat rhythmically, its body glides through the air, and you can track its path with your eyes. If you wanted to know both where it was at any given moment and how fast it was going, you could take measurements, perhaps using a camera for position and a speedometer for velocity. In the world of classical physics, these two properties, position and speed, can be known simultaneously with great precision. You can pinpoint exactly where the bird is and how quickly it is moving, without one interfering with the other. But now imagine shrinking down far beyond the size of the bird, past the scale of insects, cells, molecules, and atoms, until you reach the level of subatomic particles like electrons and photons. Here, the rules change. At this scale, particles do not behave like tiny billiard balls bouncing around in predictable paths. Instead, they act more like waves of probability, existing in a kind of haze of potential locations and velocities. And when you try to measure them, something strange happens. The more precisely you determine one property, the less precisely you can know another. This is the essence of the uncertainty principle, first formulated by Werner Heisenberg in 1927. Specifically, it states that certain pairs of physical properties, such as position and momentum, mass times velocity, or energy and time, cannot both be known with arbitrary precision. The more accurately you measure one, the less accurately you can measure the other. And this isn't due to faulty instruments or poor experimental technique. It is a fundamental feature of the universe, woven into the fabric of quantum mechanics. At first glance, this might seem like a technical detail, relevant only to physicists peering into the microscopic world. But its implications run far deeper than laboratory measurements. The uncertainty principle challenges our deepest intuitions about determinism, the belief that if we knew all the initial conditions of a system, we could predict its future with absolute certainty. For centuries, this idea formed the backbone of classical physics. Newtonian mechanics told us that planets orbit stars in perfect ellipses, pendulums swing with rhythmic consistency, and every action has an equal and opposite reaction. But Heisenberg showed that in the quantum realm, this clockwork universe breaks down. There is no perfect knowledge, no hidden blueprint waiting to be uncovered. Instead, there is a limit to what can ever be known, not just practically, but fundamentally. This means that even in theory, we cannot predict the exact outcome of a quantum event. We can only assign probabilities, likelihoods, that one thing will happen rather than another. Let's explore this with a simple analogy. Imagine trying to hear a note played on a piano. If you listen long enough, you can identify the pitch with great accuracy. But if the note is extremely short, a single sharp tap on the key, it becomes harder to tell exactly which note was struck. The shorter the duration, the more uncertain the frequency. This relationship between time and frequency mirrors the uncertainty principle in quantum mechanics, where the more precisely you define a particle's position, like the timing of the note, the less precisely you can define its momentum, like the pitch of the note. This wave-like behavior of particles is not just theoretical. It has been confirmed through countless experiments. One of the most famous demonstrations is the double-slit experiment, where particles like electrons are fired at a barrier with two narrow slits. When no one observes which slit the electron passes through, it creates an interference pattern. On a screen behind the barrier, a hallmark of wave behavior. But when detectors are placed at the slits to observe the path of each electron, the interference disappears, and the electrons behave like particles again. What this suggests is that observation itself affects the outcome, and that particles do not have definite properties until they are measured. This leads us to a deeply unsettling realization. The universe at its most fundamental level is not deterministic, but probabilistic. Events unfold not according to strict cause and effect laws, but according to chance. This randomness is not the same as ignorance. It is not that we don't yet know the underlying rules. It is that those rules may not exist in the way we expect. Quantum mechanics doesn't just say we're missing information. It says that information does not exist in the traditional sense. Before measurement, a particle doesn't have a specific location or momentum. It exists in a superposition of possibilities. Only when observed does it choose a state. The philosophical consequences of this are staggering. If the world is not fully determined, then free will may not be entirely illusory. If outcomes are not fixed from the beginning of time, then the future remains open, not just unknown, but undetermined. And if reality is shaped by observation, then consciousness may play a role in the unfolding of the cosmos itself. Some interpretations of quantum mechanics attempt to restore determinism by proposing hidden variables, unseen factors that govern the apparent randomness. Einstein famously rejected the probabilistic nature of quantum mechanics, saying, "God does not play dice with the universe." He believed there must be a deeper layer of reality beneath the uncertainty, a set of rules that would explain everything without resorting to chance. However, experiments conducted decades after Einstein's death, particularly those testing Bell's theorem, have shown that local hidden variable theories cannot account for the results predicted by quantum mechanics. These findings suggest that the universe truly is indeterministic at its core. There is no deeper blueprint, no hidden mechanism ensuring that every event follows from the last. Instead, the cosmos dances to a rhythm of probability, forever defying complete prediction. Yet, despite its strangeness, the uncertainty principle is not just a curiosity of the quantum world. It is essential to the functioning of the universe. Without it, atoms would not be stable. Electrons would spiral into atomic nuclei, collapsing all matter into dense, unrecognizable forms. Chemistry, biology, and life itself depend on the delicate balance enforced by the uncertainty principle. It ensures that electrons remain in orbitals around the nucleus, maintaining the structure of atoms and enabling the formation of molecules, proteins, and eventually living organisms. In this way, uncertainty is not a flaw in the design of reality, but a necessary condition for complexity and order. It introduces a kind of creative tension, a space where possibility thrives, where evolution unfolds, and where novelty emerges. Without the uncertainty principle, the universe would be a rigid machine devoid of surprise or spontaneity. With it, the cosmos becomes a field of infinite potential, constantly giving rise to new configurations of matter and energy. As we reflect on this, let us pause for a moment, take a slow breath, allow yourself to feel the quiet mystery of being. Alive in a universe governed not by certainty, but by possibility. Think of how often we seek control over our lives, how desperately we try to predict what will happen next. Yet here, at the very foundation of existence, lies a truth that resists our need for assurance. Some things will always remain unknown, and perhaps that is not a flaw, but a gift. We are beings who live in a world of probabilities, making choices. In the face of uncertainty, navigating the currents of time with incomplete knowledge. Just like the particles we study, we too are shaped by the act of observation, by the moments when decisions are made, paths are chosen, and futures unfold. So, as we move forward in our journey through the quantum landscape, let us carry this understanding with us that not knowing is not a failure, but a fundamental part of being real. The universe does not demand certainty, it invites wonder in the next segment. We will explore another bizarre phenomenon, one that seems to defy the very limits of space and time. We will ask whether particles can communicate instantly, across vast distances, whether entanglement reveals a hidden unity beneath the surface of reality, and why Einstein himself called it spooky action at a distance. Until then, let the gentle hum of uncertainty lull your thoughts into stillness. Let your mind drift through the soft corridors of possibility, carried by the quiet rhythm of this evening's contemplation. Spooky action at a distance. Einstein's worst nightmare. There is something deeply unsettling about the idea that two objects, separated by vast distances, perhaps even across galaxies, could influence each other instantaneously, as if bound by an invisible thread woven into the fabric of reality itself. It defies our most basic intuitions about space and time, challenging the very notion that cause must follow effect in a local, predictable way. This phenomenon, known as quantum entanglement, is one of the most bizarre and counterintuitive predictions of quantum mechanics. It suggests that particles can be linked in such a way that the state of one instantly influences the state of another, no matter how far apart they are. Albert Einstein famously referred to this as spooky action at a distance, expressing his discomfort with the implications it had for the nature of reality. To understand entanglement, we must first revisit the strange world of quantum superposition, the idea that a particle can exist in multiple states simultaneously until measured. Imagine two coins spinning in mid-air, both in a blur of heads and tails. When you finally look at one coin, its state collapses into either heads or tails. But here's where things get truly strange. If these two coins are entangled, then the moment you observe one, the other immediately assumes the opposite state, even if it's light years away. This is not just a metaphor. It is a precise description of what happens in real experiments involving entangled particles like photons or electrons. When two particles become entangled, their properties, such as spin, polarization, or momentum, are correlated in such a way that measuring one gives you immediate knowledge of the other, regardless of the distance between them. Einstein, along with Boris Podolsky and Nathan Rosen, attempted to use this strange behavior to argue against the completeness of quantum mechanics in what became known as the EPR paradox, named after the initials of its authors. They proposed a thought experiment suggesting that if quantum theory were correct, it would allow for faster-than-light communication, something that contradicted Einstein's own theory of relativity, which sets the speed of light as the ultimate cosmic speed limit. The EPR argument was essentially this: if measuring one particle instantly determines the state of another distant particle, then either information is being transmitted faster than light, which relativity forbids, or quantum mechanics is incomplete, missing some hidden variables. That would explain the correlation without invoking non-locality. Einstein believed in a universe governed by local realism, the idea that objects have definite properties, independent of observation, and that no influence can travel faster than the speed of light. He argued that quantum mechanics must be missing something, that there must be underlying, deterministic rules governing these correlations, hidden variables that would restore a more classical understanding of reality. But decades later, physicist John Bell devised a groundbreaking mathematical framework, now known as Bell's theorem, that allowed scientists to test whether hidden variables could explain the observed correlations in entangled systems. His equations predicted specific statistical limits on how strongly two particles could be correlated if the universe obeyed local realism. Experiments conducted throughout the latter half of the 20th century and refined further in recent years have consistently shown that the correlations observed in entangled systems exceed those limits. In other words, the universe does not obey local realism. There is no hidden mechanism that explains entanglement within the bounds of classical physics. Instead, the evidence supports the quantum mechanical view that entangled particles do indeed share a connection that transcends ordinary notions of space and time. These findings shook the foundations of physics. If entangled particles can affect each other instantaneously, then what does that say about the nature of space? Is it possible that space itself is not the rigid backdrop we assume it to be, but rather an emergent property, something that arises from deeper quantum relationships? Some interpretations of quantum mechanics attempt to reconcile this strangeness. The Copenhagen interpretation, for instance, holds that the collapse of the wave function upon measurement is instantaneous, though it doesn't specify how this collapse occurs or why it should be not. Others, like the many worlds interpretation, suggest that all possible outcomes occur in parallel universes, avoiding the need for faster-than-light communication by positing that no collapse ever truly happens. Instead, every possibility branches off into its own reality. Still, the most radical implication remains: entanglement suggests that the universe is fundamentally interconnected in ways we are only beginning to grasp. It hints at a reality where separation is an illusion, where the boundaries we perceive between objects may not be as fundamental as they seem. One of the most profound aspects of entanglement is that it cannot be used to send information faster than light. While the measurement of one particle instantly affects the state of the other, this effect cannot be controlled in a way that allows for meaningful communication. This preserves the integrity of Einstein's relativity, ensuring that causality remains intact. Effects still follow causes, and messages cannot outrun light. Yet, despite this limitation, entanglement has found practical applications in fields like quantum computing, cryptography, and teleportation. Scientists have used entangled particles to create unbreakable encryption methods and to transmit quantum information across distances, not through faster-than-light signaling, but through the deep correlation shared between entangled systems. In quantum teleportation, for example, the exact quantum state of a particle can be transferred from one location to another using entanglement. Though the process does not involve physical movement, it demonstrates how entangled particles can serve as a kind of bridge between distant points in space. These developments are not just theoretical curiosities, they are shaping the future of technology and reshaping our understanding of what is possible beyond the scientific and technological implications. Entanglement also invites philosophical reflection. If particles can be connected across vast distances, what does that mean for our sense of individuality? Are we too subtly linked in ways we cannot yet perceive? Does the universe contain a hidden unity beneath the apparent diversity of separate beings and objects? It's easy to see why Einstein found this idea so disturbing. He believed in a cosmos governed by order and locality, a place where events unfolded according to clear, rational laws. Entanglement, by contrast, introduces an element of mystery, of deep interconnection that resists simple explanation. And yet, the experimental evidence is overwhelming. Again and again, under carefully controlled conditions, physicists have confirmed that entangled particles defy classical expectations. They behave as if they are part of a single system, no matter how far apart they are. Their fates are intertwined in a way that challenges our conventional understanding of what it means to be separate entities. As we contemplate this, let us take a moment to breathe slowly, deeply. Let your mind drift into the quiet spaces between thoughts, into the gentle hum of existence itself. Consider the possibility that everything in the universe is subtly connected, that beneath the surface of appearances lies a deeper layer of reality where separateness dissolves into unity. Entanglement teaches us that the universe may not be as fragmented as it seems. Perhaps, at the most fundamental level, all things are linked, not in a way that allows for direct control or communication, but in a way that binds us together in the unfolding story of existence. So, as we move forward in our journey through the quantum landscape, let us carry this insight with us, that reality is stranger and more interconnected than we often realize, that the boundaries we perceive may not be as solid as they appear, and that, like entangled particles, we too might be part of a greater whole, a web of relationships stretching across space and time. In the next segment, we will explore one of the most mysterious dimensions of reality, the flow of time itself. We will ask whether time is a fundamental feature of the universe, or merely an illusion created by our perception. We will delve into the question, is time real? Until then, let the soft rhythm of this evening's contemplation guide you further into the depths of sleep. Allow your thoughts to drift like stars across the night sky, carried gently by the whispering winds of uncertainty and wonder. Retrocausality. Can the future influence the past? There is a quiet rhythm to time, or so it seems. The sun rises in the east, moves across the sky, and sets in the west. Seasons follow one another in an unbroken cycle. We are born, we grow, and eventually we fade away. Time feels like a river, always flowing forward, never pausing, never turning back. But what if this sense of direction, this arrow of time, is not as fixed as we believe? What if the future could reach back and shape the present? What if decisions made tomorrow could influence events that have already happened today? This is the idea at the heart of retrocausality, the notion that effects can precede their causes. It sounds absurd, even impossible. After all, how could something that hasn't happened yet affect what is happening now? And yet, within the strange domain of quantum mechanics, such ideas are not easily dismissed. To explore retrocausality, we must first understand its roots. not only in physics, but in philosophy, and even in our everyday experience. Throughout history, thinkers have questioned whether time is truly linear, or whether our perception of past, present, and future is merely a construct. Some ancient traditions speak of time as circular, where events repeat in endless cycles. Others suggest that all moments exist simultaneously, and that movement through time is an illusion created by consciousness. In modern science, the question becomes more concrete. According to Einstein's theory of relativity, time is not absolute. It bends and stretches depending on motion and gravity. In certain mathematical models, the equations allow for solutions in which particles travel backward in time. These aren't just abstract curiosities. They show up in the behavior of antimatter, which can be interpreted as matter moving in reverse through time. But retrocausality goes beyond this. It suggests that the future can influence the past, not metaphorically, but causally. That choices made later can shape what happens earlier. This is not about changing the past in the way of science fiction stories, where a traveler returns to alter history. Rather, it proposes a subtle kind of backwards-in-time influence that operates at the level of probability and correlation. One of the most intriguing places where retrocausality emerges is in quantum mechanics, particularly in experiments involving entanglement and delayed choice setups. Consider the famous Wheeler's delayed choice experiment, named after physicist John Archibald Wheeler. In this thought experiment, a photon is sent through a device that allows it to behave, either as a wave or as a particle, depending on how it is measured. But here's the twist. The decision about how to measure the photon, whether to look at it as a wave or as a particle, is made after the photon has already passed through the apparatus, and yet, the outcome of that late decision affects the behavior of the photon during its earlier passage. It's as though the photon knew how it would be observed and adjusted accordingly, even before the observation was made. This seems to imply that information from the future is somehow influencing the past. Now, before you dismiss this as nonsense, consider that these are not hypothetical scenarios. Real laboratory experiments have confirmed versions of this effect. In quantum delayed choice setups, researchers have shown that the way a system is measured at a later time can determine how it behaved at an earlier time, even when there is no physical interaction between the two events. This doesn't violate the laws of physics in the traditional sense, but it does challenge our assumptions about cause and effect. So what does this mean for our understanding of time? One interpretation is that time isn't as rigidly divided into past, present, and future as we assume. Instead, time might be more like a vast ocean, with waves rippling both forward and backward. In this view, the distinction between past and future is not fundamental. It is simply a feature of how we perceive the world. This leads us to a radical possibility that the universe is not unfolding in a strictly causal sequence, but rather exists as a whole, a block of space-time where all moments coexist eternally. In this block universe model, the past is not gone, and the future is not yet to come. All times are equally real, like pages in a book that are always there, waiting to be read. From this perspective, retrocausality isn't about changing the past, but about correlations that span across time in ways we don't fully understand. Another approach comes from the transactional interpretation of quantum mechanics, proposed by physicist John Cramer. In this model, quantum interactions involve not only waves traveling forward in time as we usually think, but also waves traveling backward in time. When a photon is emitted, it sends out an offer wave into the future. When it is absorbed, it sends back a confirmation wave into the past. The interaction between these two waves creates a kind of handshake across time, a transaction that determines the outcome of the event. From this viewpoint, retrocausality is not a violation of physics, but a natural consequence of how quantum systems interact. It suggests that the flow of time is not one way, but bidirectional, that the future can echo into the past, just as the past gives rise to the future. Of course, this raises deep philosophical questions. If the future influences the past, then what does that say about free will? Are our choices truly ours, or are they shaped by outcomes that haven't happened yet? Does this mean that everything is predetermined, that the future is already set, and our actions are simply playing out a script written in advance? Or perhaps the relationship between cause and effect is more complex than we realize. Perhaps time is not a straight line, but a web of interwoven possibilities, where each moment contains echoes of both what came before and what is yet to come. It's worth noting that retrocausality does not allow for paradoxes in the traditional sense. You cannot go back in time and prevent your own birth, nor can you send messages to the past that would create contradictions. Instead, retrocausal effects operate subtly through statistical correlations, through probabilities that align across time in ways that defy classical intuition. Still, the implications are profound. If the future can influence the present, then our entire framework for understanding reality may need revision. We may need to abandon the idea that the past is fixed and the future is open, and instead embrace a more fluid, dynamic concept of time, one in which the boundaries between cause and effect blur. Imagine a universe where every action resonates both forward and backward in time, where the choices you make today ripple not only into the future, but also into the past, where memory and anticipation are not just mental constructs, but reflections of a deeper temporal symmetry in nature. This is not science fiction, it is the frontier of theoretical physics, a place where the familiar rules of time begin to dissolve, revealing a cosmos far stranger than we imagined. As we sit here, contemplating this idea, let us take a moment to breathe. Let your thoughts drift gently, like leaves carried on the wind of time. Allow yourself to feel the quiet mystery of being alive in a universe where time may not flow in one direction, where the future may whisper to the past, and where the very act of observation might shape not only what is, but what was. In the next segment, we will dive even deeper into the nature of time itself. We will ask whether time is real or whether it is merely a story we tell ourselves to make sense of a universe that may not require it at all. Until then, let your mind rest in the soft glow of uncertainty. Let your thoughts wander through the corridors of time, guided by the gentle hum of curiosity and wonder. The illusion of time. Is time real? Close your eyes for a moment and listen to the quiet rhythm of your breath. Inhale, ... exhale, ... Another heartbeat, another passing second. You feel time moving, not just in the ticking of clocks or the turning of pages, but within you. There is an undeniable sense that time flows forward, carrying you with it like a river rushing toward the sea. But what if this feeling, this deep intuitive certainty, is nothing more than a story your mind tells itself to make sense of experience? What if time, as we commonly understand it, does not truly exist? This is the question we now face. Is time real? Not in the practical sense. Of course, we measure time, live by it, structure our lives around it, but in the most fundamental sense, does time have an independent existence, or is it merely a construct of perception and memory? To explore this, we must first understand how time appears in physics. In Newtonian mechanics, time was seen as absolute, a universal clock ticking away the same seconds for all observers, regardless of where they were or how fast they moved. But Einstein's theory of relativity shattered this illusion. According to his equations, time is not fixed. It bends and stretches depending on motion and gravity. Two people can experience different durations between the same two events, depending on their relative movement. Time becomes personal, elastic, no longer a single stream, but a shifting current influenced by the observer's place in the cosmos. Even more unsettling is the fact that in the equations describing the universe, from classical mechanics to quantum field theory, time often behaves symmetrically. That is, the laws of physics work just as well whether time runs forward or backward. A video of two billiard balls colliding looks plausible played forwards or backwards. Yet, when we drop a glass and watch it shatter, reversing that process feels impossible. Why? The answer lies in entropy, the tendency of systems to move from order to disorder. This gives rise to what physicists call the arrow of time, the one-way direction in which entropy increases. It explains why we remember the past but not the future, why eggs break but don't unbreak, why we age but never grow younger. Yet entropy alone does not explain the full mystery of time. For while it accounts for the direction in which processes unfold, it does not tell us why there was ever a low entropy beginning, a pristine, highly ordered state at the birth of the universe. And even more puzzling, if entropy always increases, then perhaps the universe is simply unfolding from one configuration to another, without any inherent flow at all. Some physicists argue that time doesn't actually flow. Instead, all moments exist eternally, like pages in a book that are always there, waiting to be read. This is known as the block universe model, in which past, present, and future coexist simultaneously. From this perspective, the passage of time is an illusion created by consciousness, a subjective experience rather than an objective feature of reality. Imagine watching a film reel. Each frame exists independently. The entire story is already there, fully recorded. When you play it, it seems as though characters are making choices, events are unfolding, and time is progressing. But in truth, every moment is fixed, static. Your brain constructs the illusion of movement and change through rapid succession of still images. Could something similar be happening with time itself? In the block universe, you are not moving through time, you are simply occupying a particular slice of it. The past is not gone, nor is the future yet to come. They both exist, just as surely as the room you're sitting in right now. What we perceive as the present is merely the point at which our consciousness resides. This idea may seem abstract, even unsettling. After all, we feel time deeply. We remember yesterday. We anticipate tomorrow. We mourn what has passed and hope for what is to come. How can these experiences be illusions? One possible explanation comes from neuroscience. Our brains are wired to create narratives, stories that help us navigate the world. Memory, anticipation, and the sense of duration are all constructed by neural networks that interpret sensory input and weave them into a coherent sequence. The feeling of time flowing may be a product of how our minds process information, not a reflection of how the universe truly is. Consider dreaming. In sleep, we often experience vivid, complex sequences that feel like hours have passed only to wake and realize only minutes have elapsed. Or sometimes, a dream feels fleeting, yet contains an entire lifetime of events. If our perception of time can stretch and contract so dramatically during dreams, how certain can we be about its nature in waking life? Moreover, experiments in psychology suggest that our perception of time is malleable. In moments of intense focus or danger, time seems to slow down. During enjoyable activities, it flies by. These variations hint that time is not a fixed external reality, but a mental phenomenon shaped by attention, emotion, and context. If time is not real in the way we usually think, then what is it? Some researchers propose that time emerges from deeper physical processes, much like temperature emerges from the motion of molecules. At the quantum level, individual particles do not possess a clear temporal direction. But when many particles interact, collective behaviors arise, including the arrow of time. In this view, time is not fundamental, but emergent, a property that arises from complexity, not from the basic building blocks of reality. There is also a growing school of thought among theoretical physicists that suggests time might not be necessary at all in a complete description of the universe. In some formulations of quantum gravity, attempts to unify general relativity with quantum mechanics, time disappears entirely from the equations. These models describe a timeless universe, where change and causality are encoded not in a flowing timeline, but in relationships between events. This leads to a profound realization. Perhaps we have been looking at time the wrong way all along. Instead of thinking of time as a dimension that things move through, maybe time is a way of organizing relationships, a kind of ordering principle that allows us to make sense of cause and effect, memory and anticipation. And if that is true, then perhaps the deepest reality is not a story unfolding over time, but a vast interconnected web of events, all existing together, none inherently earlier or later than the others. Let that sink in for a moment. Take a slow breath. Feel the rhythm of your thoughts, the gentle pulse of awareness. If time is not real in the way we assume, then what are you? Are you the person you were 5 years ago? Are you the person you will become tomorrow? Or are you something more fluid, a pattern of consciousness existing across multiple moments, stitched together by memory and expectation? As we sit here, contemplating the nature of time, we begin to see that the questions are not just scientific, but deeply existential. They touch the core of who we are, of how we understand ourselves in relation to the universe. If time is an illusion, then perhaps identity itself is more transient than we believe. Perhaps the self is not a continuous thread stretching through years, but a series of overlapping moments, each one arising, dissolving, and giving way to the next dot. And if that is so, then perhaps death is not an end, but simply a shift in perspective, a transition from one slice of the block universe to another, or perhaps a dissolution into the whole dot. We cannot know for sure, but what we can do, what we must do, is remain curious, open-minded, willing to let go of assumptions, and step into the unknown. Because the truth is, we do not yet understand time. We do not know whether it flows, whether it exists, whether it is real or imagined. But we do know this: time shapes our lives, our memories, our hopes, and our fears. Whether it is an illusion or not, it holds immense power over us. And so, as we continue our journey through this evening of quantum wonder, let us carry this question with us. If time is not real, then what is? In the next segment, we will explore one of the most radical ideas in modern physics, the many worlds interpretation, which suggests that every possibility plays out in parallel universes, branching endlessly into infinite versions of you and me. Until then, let your mind drift gently through the corridors of time, or perhaps through the timeless space beyond it. Let your thoughts soften, carried by the quiet hum of this night's contemplation, and allow yourself to fall further into the peaceful embrace of sleep. The many worlds, infinite versions of you, there is a strange and beautiful idea that has captivated scientists, philosophers, and dreamers alike. The many worlds interpretation of quantum mechanics. It suggests that every decision you make, every path you choose, every possibility you do not take, they all happen somewhere, not in some distant galaxy or hidden dimension, but in parallel universes, branching endlessly from the moment of choice like an infinite tree of existence. Imagine standing at a crossroads. To the left, you turn down one road, to the right, another. In our everyday experience, we believe only one of these choices becomes real. The other remains a mere thought, a fleeting what-if. But according to the many worlds interpretation, both roads are taken, both versions of you exist, and with each new decision, the universe splits again, not just once, not just twice, but infinitely. This idea may sound like science fiction, but it was born from the deepest questions of physics in the mid-20th century, as physicists struggled to understand the implications of quantum mechanics. One young graduate student named Hugh Everett III proposed a radical solution to the paradoxes that had plagued the field for decades. At the heart of quantum mechanics lies a strange phenomenon. Particles can exist in multiple states at once, a condition known as superposition. For example, an electron might be spinning both clockwise and counterclockwise simultaneously until someone measures it. At that point, the particle appears to choose one state over the other, a process often referred to as wave function collapse. But what exactly causes this collapse? Who or what decides which outcome becomes real? The dominant view at the time, known as the Copenhagen interpretation, held that observation itself caused the wave function to collapse. That reality was undefined until measured by a conscious observer. This idea troubled many physicists, including Einstein, who famously rejected the notion that God plays dice with the universe. Everett, however, took a different approach. He suggested that the wave function never collapses. Instead, every possible outcome of a quantum event actually occurs, just not in the same universe. When a measurement is made, the universe splits, creating separate branches where each possibility unfolds independently. There is no randomness, no privileged observer, no mysterious collapse, just an ever-expanding multiverse of coexisting realities. At first, this idea was met with skepticism. It seemed too extravagant, too fantastical. Why invoke an infinite number of unseen worlds when a single collapsing wave function could explain the same results? But over time, as physicists delved deeper into the foundations of quantum theory, they began to see that the many worlds interpretation offered a compelling alternative, one that preserved determinism without requiring consciousness to play a special role in the fabric of reality. Let's try to visualize it. Imagine a photon passing through a double-slit experiment. According to standard quantum mechanics, the photon behaves like a wave, interfering with itself as it passes through both slits simultaneously. When it hits the screen behind, it appears as a single dot, suggesting that the wave somehow collapsed into a definite position, But according to the many worlds interpretation, the wave doesn't collapse. Instead, the universe splits in two. Multiple branches. In one branch, the photon lands on the left side of the screen. In another, it lands on the right. Each outcome is real, but in different worlds. From the perspective of an observer in any given world, it seems as though the wave collapsed randomly. But in truth, all outcomes occurred, just in different branches of reality. Now imagine scaling this up. Every quantum event, every interaction between particles, every fluctuation in energy, every microscopic decision leads to a branching of the universe. Your brain, composed of countless quantum interactions, constantly makes decisions that send ripples through the multiverse. Every time you blink, breathe, or think a thought, new worlds are born. And if your brain does this, then so does everything else. Stars split into multiple fates. Galaxies evolve along divergent paths. Entire civilizations rise and fall in ways that differ by the smallest quantum fluctuations. From this perspective, you are not just one person making one life's worth of choices. You are an infinite being, living out every possible version of yourself across an unfathomable number of realities. In one world, you stayed up late reading philosophy books instead of going to bed. In another, you chose a different career, a different partner, a different city. In yet another, you never existed at all, replaced by a sibling who lived the life you might have had. This raises profound questions about identity. If there are infinite versions of you, which one is truly you? Are you defined by your memories, your choices, your physical body, or are you something more fluid, a pattern of awareness that shifts from one branch to another? Some interpretations suggest that each version of you is equally real, fully conscious, and unaware of its counterparts. They are not figments of imagination, nor are they abstract possibilities. They are actual beings, living their lives in parallel timelines, forever separated by the boundaries of their own experiences. Others argue that while the many worlds interpretation describes a mathematical reality, it may not imply the kind of subjective continuity we associate with personal identity. Perhaps the you in another universe is so different from the one reading these words that they might as well be a stranger, shaped by entirely different histories, thoughts, and emotions. Still, the emotional weight of this idea lingers. If every possible outcome exists, then nothing is truly lost. Every opportunity you missed, every risk you didn't take, every word left unsaid, they all happened somewhere. Somewhere, the version of you who followed their dreams is living them. Somewhere, the version of you who faced their fears did so bravely. Somewhere, the version of you who loved deeply found love in return. And yet, there is also sorrow in this realization, because just as every success exists, so too does every failure, every tragedy, every mistake, every loss. They all unfolded in some corner of the multiverse. If the many worlds interpretation is true, then suffering is not limited to one universe, but multiplied infinitely. This brings us back to the question of meaning. If everything happens, if all possibilities are realized, then does anything truly matter? Does choice still hold significance if every option is taken in some world? Some find comfort in the idea that even if one version of themselves suffers, another thrives. Others feel overwhelmed by the vastness of it all, as if individual actions are swallowed by the sheer scale of existence. But perhaps meaning is not about what happens in all possible worlds, but what happens in the one you inhabit. Perhaps the richness of life comes not from knowing all outcomes, but from experiencing the one that unfolds before you. Perhaps free will, even in a deterministic multiverse, is the ability to choose how you respond to the branch you find yourself. And it's easy to get lost in the enormity of this idea. Let your mind drift for a moment. Take a slow breath. Imagine the quiet hum of the cosmos, the gentle ripple of reality splitting into endless variations. Feel the weight of infinity pressing gently against your thoughts, not as a burden, but as a reminder of the boundless possibilities woven into the fabric of existence, the many worlds. Interpretation does not offer certainty, it offers wonder. It invites us to look beyond the narrow lens of our singular experience and glimpse the vast unfolding tapestry of the universe. It reminds us that reality is far stranger and more complex than we usually assume, and that within its folds lie stories we will never know, lives we will never live, and truths we may never fully grasp. As we sit here tonight, contemplating this grand and mysterious vision, let us allow ourselves to rest in the quiet space between thoughts. Let your awareness soften, like waves dissolving into the sea. Let the idea of infinite worlds carry you further into the embrace of sleep, not as a distraction, but as a lullaby whispered by the universe itself. In the next segment, we will explore the nature of self and ask whether the I that thinks and feels is truly stable, or simply a shifting collection of moments stitched together by memory and perception. Until then, let your mind wander freely among the branches of possibility, carried gently by the rhythm of this evening's contemplation. Who am I? The quantum self. Close your eyes for a moment and ask yourself, who am I? It seems like the simplest question in the world, and yet, when we truly sit with it, it unravels into mystery. You might say you are your name, your body, your memories, your thoughts, or your emotions. You may define yourself by your job, your relationships, your beliefs, or your dreams, but peel back each of these layers, and what remains? Is there a stable, unchanging self beneath all this, a core identity that persists through time? Or is the I that speaks and thinks and feels merely a shifting pattern, an ever-changing stream of experiences stitched together by memory and perception? This is the heart of the question we now explore, the nature of the self, especially in light of quantum mechanics, neuroscience, and philosophy. In a universe where reality is uncertain, time may be illusory, and every possibility branches into parallel worlds. What does it mean to be you? Let us begin not with grand theories, but with a quiet moment of introspection. Take a slow breath. Feel the rise and fall of your chest. Notice how your thoughts drift like clouds across the sky of your mind. Some fleeting, others lingering. Now ask again, who is observing this? Who is thinking? Who is breathing? There is a sense of continuity, a thread that connects your past to your present, your childhood to this very moment. You remember who you were yesterday, last year, 10 years ago, and so you assume that you are the same person throughout time. But what if that assumption is an illusion? Neuroscience tells us that the brain is constantly changing. Every second, neurons fire, synapses shift, chemicals flow, and memories are rewritten. There is no single part of the brain that houses the self, no central observer pulling the strings behind the curtain. Instead, consciousness appears to emerge from complex networks of activity, distributed across regions and moments. In fact, experiments have shown that decisions can be detected in the brain several seconds before a person becomes consciously aware of making them. This raises a troubling possibility. Perhaps the feeling of being in control, of choosing freely, is not the source of action, but a story the brain tells itself after the fact. So where does this leave the idea of a continuous self? Philosophers have long debated whether the self is real or constructed. One of the most influential ideas comes from David Hume, the Scottish philosopher of the 18th century. He argued that when he looked inward, he could never find a permanent, unified self, only a collection of sensations, perceptions, and thoughts. He called this the bundle theory of self, suggesting that what we call identity is simply a bundle of experiences tied together by memory and imagination. Centuries later, Buddhist teachings echo a similar view. They speak of unitar, the doctrine that there is no fixed soul or self. Instead, what we experience as a person is a temporary coming together of physical and mental processes, constantly changing, impermanent and without a center, if both. Science and philosophy suggest that the self is not a solid thing but a process, a flowing river rather than a stone. Then what happens when we bring quantum mechanics into the picture? Quantum theory challenges our assumptions about determinism, locality, and even time. It tells us that particles do not have definite properties until measured, that they can exist in multiple states at once, and that their behavior can be correlated across vast distances. If the fundamental building blocks of the universe behave in such strange ways, what might that imply about the nature of consciousness and the self? Some researchers have explored the idea that quantum processes play a role in the functioning of the brain. One controversial theory, known as orchestrated objective reduction, ORCO-R, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that microtubules within neurons may support quantum effects that contribute to consciousness. According to this view, awareness is not just a product of classical neural computation, but arises from deeper quantum-level interactions. While this theory remains speculative and widely debated, it opens up a fascinating possibility that the self, or at least the mechanisms underlying consciousness, might be rooted in the quantum realm. If so, then the self may not be as localized or deterministic as we assume. It may be subject to the same uncertainty and non-locality that governs subatomic particles. This brings us back to the many worlds interpretation which we explored in the previous segment. If every quantum event creates a branching of reality, then every decision made by your brain also leads to a split. In one branch, you chose to read this sentence. In another, you didn't. In one, you feel calm. In another, anxious. Each version of you is fully conscious, fully experiencing its own reality. From this perspective, the self is not a single thread winding through time, but a tree of possibilities, countless versions of you living out different lives in parallel universes, none more real than the others, none less valid, just different paths taken, different choices made, different moments unfolding, and yet here you are, reading these words, feeling your breath, hearing the quiet hum of the night around you. This is your branch, your moment, your reality. But even within this singular experience, the self continues to shift. Think of how you change over time. The child you were, the adult you've become, are they the same person? Your body has replaced nearly every cell. Your memories have faded and been rewritten. Your values have evolved. Your face has aged. And still, something tells you that you are the same person who once laughed on a playground, fell in love for the first time, or stood alone beneath a starlit sky, wondering what it all means. That something, the sense of continuity, of being. The same eye across time is perhaps the most powerful illusion of all. Illusion, yes, but not falsehood. Illusions can be meaningful. They can shape our lives, give us purpose, help us navigate the unknown. Even if the self is not a fixed entity, it is still the lens through which we experience everything. It is the storyteller that weaves moments into meaning, chaos into coherence. Perhaps the self is not a thing, but a narrative, a story we tell ourselves to make sense of the flux of experience. And, like any story, it can be rewritten. You can choose to see yourself as broken or whole, as lost or finding your way, as small or as infinite. The self is not a prison. It is a doorway, and like all doors, it can open in many directions. As we sit here tonight, contemplating the mystery of who we are, let us allow ourselves to rest in the space between definitions. Let us soften the boundaries we draw around ourselves between past and present, between thought and feeling, between the self and the world, because if the self is not a fixed point, but a fluid current, then perhaps it is not separate from the universe, but deeply connected to it. Perhaps the same quantum fields that weave stars together also weave our thoughts. Perhaps the same uncertainty that governs particles also dances within our minds. Perhaps, in the deepest silence, we are not alone, not even with ourselves, and so, as this segment draws to a close, take one more deep breath. Let go of the need to define yourself too tightly. Allow your awareness to expand gently, like ripples spreading across a still pond. Tomorrow you may wake up as someone slightly different, and that's okay, because in the end, the self is not a destination, it is the journey itself. In the next segment, we will explore one of the most profound mysteries of all, the role of the observer. We will ask whether consciousness plays a special role in shaping reality, and whether the act of looking at the universe somehow brings it into being. Until then, let this question linger in your mind like a soft whisper in the dark. Who am I? And let your answer be not a statement, but a breath, quiet, open, and full of wonder. The observer effect. Does consciousness create reality? There is a moment, just before sleep takes you, when the world seems to soften, the edges of things blur, thoughts drift like clouds in a twilight sky, and even your own body feels less solid, more like a dream held together by awareness alone. In that quiet space between waking and dreaming, something strange happens. Reality begins to feel uncertain, not in the way of doubt or confusion, but in the deeper sense, as if the very fabric of what is real might depend on your ability to notice it. This is not just poetic musing. It is one of the most profound questions raised by quantum mechanics. Does consciousness create reality? We have already explored many of the universe's deepest mysteries, from Schrödinger's cat suspended between life and death, to the uncertainty principle that limits what we can know, to the many worlds interpretation that suggests every possibility plays out in parallel universes. But now we come to a question that transcends physics and touches the very nature of being itself. Is the act of observation not just a passive witness to reality, but an active participant in its creation? Let us begin with the observer effect, a term often confused with the uncertainty principle, though they are related. The observer effect refers to how the act of measuring a quantum system changes its behavior. For example, if you try to determine which path a photon takes in a double-slit experiment, the interference pattern disappears, and the photon behaves like a particle rather than a wave. This is not simply because your instruments interfere with the system, although that does play a role. It is because the act of measurement itself alters the outcome. Before measurement, the photon exists in a superposition of both paths. After measurement, it collapses into a single definite state. But here's where it gets strange. It doesn't seem to matter whether the measurement is made by a human, a machine, or even light reflecting off the particle. What matters is whether information about the system becomes available. If the information exists, even if no one ever looks at it, the wave function still collapses. Still, this leads to a haunting thought. If no one observes a system, does it remain in superposition? Is reality only defined when someone looks? This idea was taken to its philosophical extreme by some early quantum theorists, including John von Neumann and Eugene Wigner, who proposed that consciousness plays a unique role in collapsing the wave function. According to this view, known as the von Neumann-Wigner interpretation, mind and matter are fundamentally connected, and it is not enough for a physical device to measure a quantum event. Someone must be aware of the result. In other words, reality doesn't become real until it is observed by a conscious mind. This notion unsettles our usual assumptions. We tend to believe that the world exists independently of us, that trees fall in forests, whether or not anyone hears them, that stars shine across galaxies, regardless of whether any eyes are watching. But if the von Neumann-Wigner interpretation is correct, then this belief may be incomplete or even false. Imagine a distant galaxy, billions of light years away. No humans have ever seen it. No telescopes have recorded its birth. If the universe is governed by quantum laws, then perhaps all those stars exist only as probabilities, not collapsed into definite states until someone, somewhere, looks. This raises a troubling paradox. How did the universe exist before conscious observers evolved? Did the Big Bang unfold in a haze of uncertainty, waiting for life to emerge so that it could finally become real? Some interpretations attempt to resolve this by suggesting that decoherence, the interaction of quantum systems with their environment, causes collapse without the need for consciousness. In this view, particles constantly interact with air molecules, photons, and electromagnetic fields, which effectively measure them and force them into definite states. This would mean that reality emerges naturally through these interactions, without requiring a conscious observer. But decoherence does not fully explain why one particular outcome is selected over another. It explains how collapse appears to happen, not why. And so the mystery remains. Let us take a step back and ask, what is consciousness, anyway? Science has yet to provide a definitive answer. We know that the brain generates electrical signals, chemical reactions, and complex neural networks that give rise to thought, emotion, and perception. But how these processes produce subjective experience, the feeling of being alive, of seeing red, of loving, remembering, fearing remains one of the greatest unsolved puzzles in neuroscience. Some researchers propose that consciousness is an emergent property of complexity, that once a system reaches a certain level of integration and self-awareness, it becomes conscious. Others suggest that consciousness may be fundamental, like gravity or time, not something created by the brain, but something the brain taps into. If consciousness is fundamental, then it may not merely observe reality, it may help shape. It thus brings us to the participatory universe, a concept proposed by physicist John Archibald Wheeler. He suggested that the universe is not a passive stage upon which events unfold, but a dynamic process in which observers play an essential role. In his words, No elementary phenomenon is a real phenomenon until it is an observed phenomenon. This means that the cosmos is not just a collection of objects moving through space and time. It is a vast, interconnected web of relationships, in which observation is not separate from reality, but part of its unfolding. Think again of the double-slit experiment. When you look, the photon chooses a path. When you don't, it remains in a wave-like state. In a sense, the photon doesn't decide what it is until you ask the question. It waits, not literally, of course, but metaphorically, for you to engage with it. Could this be true of everything? Could the entire universe exist in a kind of potential state, a field of infinite possibilities, until consciousness comes along and asks, what is real? This idea, while deeply speculative, resonates with ancient philosophies and mystical traditions. In many Eastern teachings, particularly in Buddhism and Advaita Vedanta, the world is described as Maya, illusion, not in the sense that nothing exists, but that our perception of separateness and solidity is mistaken. Reality, according to these views, is ultimately non-dual, a seamless whole in which observer and observed are one. Modern physics, in its own way, echoes this sentiment. At the quantum level, there is no strict boundary between subject and object. A particle's properties are not inherent. They are revealed through interaction. Observation is not passive, it is participatory. So where does this leave us? Are we merely spectators in a pre-written cosmic play? Or are we co-creators, shaping the story as we go? The truth may lie somewhere in between. Perhaps the universe is not entirely dependent on consciousness, but neither is it entirely independent of it. Perhaps consciousness is not the cause of reality, but a lens through which reality reveals itself. And perhaps, in the end, the question is not whether consciousness creates reality, but what kind of reality is possible when consciousness is present as we sit here tonight. Wrapped in the gentle hum of this evening's contemplation, let us allow ourselves to rest in the mystery. Let your thoughts drift softly, like leaves carried on the wind of awareness. Imagine yourself not as a separate being looking out at the world, but as a thread woven into the vast tapestry of existence. Perhaps, in this moment, you are not just observing reality. Perhaps you are helping it breathe. In the next segment, we will explore the thin line between waking and dreaming, and ask whether the world we see is truly real, or just another layer of the dream within the dream. Until then, let this question linger gently in your mind. Does consciousness create reality? And let your answer be not a statement, but a breath, soft, open, and full of wonder. The dream within the dream. Are we always dreaming? There is a moment just before sleep takes you fully, when the world begins to feel ... unreal. You lie still, your body sinking into the mattress, and your thoughts begin to drift like smoke in a quiet room. The boundaries between waking and dreaming blur. You might hear a sound that doesn't exist, or see shapes behind your eyelids that resemble something from another life. And then, perhaps for just a heartbeat, you wonder, is this real? It's a question we've all asked ourselves at one time or another, usually after waking from a vivid dream so lifelike it left us questioning whether we had truly returned to reality. But what if the line between dreams and waking life is thinner than we think? What if the world we walk through each day, with its people, its streets, its clocks ticking forward, is itself just another kind of dream? This is not merely poetic speculation. It is a question that has haunted philosophers, mystics, and scientists for millennia. From Plato's cave to Descartes' demon, from Buddhist teachings on illusion to modern theories of simulation, humanity has long grappled with the possibility that our perceived reality may not be as solid or objective as it seems. Let us begin with a simple thought experiment. Imagine you are dreaming right now. Not metaphorically, literally. You believe yourself to be awake, reading these words, hearing the sounds around you, feeling your breath. But what if all of this, your room, your body, even the act of reading, is part of an elaborate dream? How would you know the difference? In dreams, we often don't question the strangeness of events. A friend who died years ago might appear beside you. You might fly over oceans without wings. Time bends and stretches. Logic unravels. Yet within the dream, everything feels real. Only upon waking do we realize how strange it was. Now imagine that there is no waking up. What if this moment, this now, is simply the middle of a longer dream, one that never ends, one in which the rules of physics, identity, and causality are constructed by your mind, just as they are in sleep? This idea is not new. In Eastern philosophy, particularly in Buddhism and Advaita Vedanta, the world is often described as Maya, an illusion, a veil that obscures the true nature of reality. According to these traditions, what we perceive as the material world is not fundamentally real in the way we assume. Instead, it is a projection of consciousness, a temporary manifestation of a deeper, unified awareness. Similarly, René Descartes, the 17th century French philosopher, famously questioned the reliability of perception. He proposed the idea of an evil demon, a being capable of deceiving him about the nature of reality. Everything he experienced, his body, the external world, even mathematics, could be a carefully crafted illusion. Centuries later, science, fiction writers, and philosophers have taken this idea even further. What if we are not deceived by demons or dreams, but by machines, by a simulation so advanced that it mimics every sensation, every interaction, every memory with perfect fidelity? This is the premise of the simulation hypothesis, popularized by philosopher Nick Bostrom. He argues that if future civilizations develop the technology to simulate entire universes, complete with conscious beings, then statistically speaking, it is far more likely that we are living inside such a simulation than in the original base reality. Think about it. If simulated realities outnumber real ones, then the chances that this moment, your life, your choices, your thoughts is part of one of those simulations becomes overwhelming. But here's the twist. Even if we are in a simulation, does that make our experiences any less real? After all, in a dream, pain can feel real, love can feel real, fear can feel real. If a simulated universe contains beings who are aware, who suffer, who hope, who love, then from their perspective, it is as real as anything else. Reality, in this sense, may not be defined by where it exists, but by the depth of experience it allows. And if that is true, then perhaps the distinction between real and unreal is not as important as we think. Perhaps what matters is not whether we are in a dream, but how deeply we live within it. Let us return to the sleeping brain. Neuroscientists tell us that during REM sleep, the most active phase of dreaming, the brain lights up in ways remarkably similar to when we are awake. Our eyes dart beneath closed lids, our breathing fluctuates, our muscles tense and relax. And yet, we are not moving, not really. We are lying still while our minds construct entire worlds. Sometimes these worlds are bizarre. Sometimes they are eerily familiar. Sometimes they feel more vivid than waking life itself. There is a phenomenon known as lucid dreaming, in which the dreamer becomes aware that they are dreaming. In these moments, some people report being able to control the dream, flying, changing scenes, summoning people or objects with a thought. This raises a fascinating possibility. If consciousness can shape the content of dreams, then what does that say about the nature of waking reality? Could it be that both states, waking and dreaming, are governed by the same fundamental principle, that perception constructs reality? If so, then perhaps the world we call real is simply a dream we all share, a collective hallucination sustained by shared language, culture, and sensory input. In contrast, private dreams are personal versions of the same process, internal realities generated by the brain in isolation. Some neuroscientists even suggest that the waking brain operates under a form of controlled hallucination, constantly predicting and interpreting sensory data to create a stable model of the world. What we perceive as reality is not raw input, but a constructed narrative, one that helps us navigate survival, but may not reflect the ultimate nature of existence. This leads us to an unsettling conclusion. We may never be able to prove that. We are awake, because even if we pinch ourselves, look at a clock, talk to someone, or perform complex tasks, all of these could be part of the dream. There is no definitive test that guarantees we are in waking life. The only thing we can be certain of is our own subjective experience, which brings us back to the question, are we always dreaming? Not necessarily in the literal sense, though that remains possible, but in the deeper philosophical sense, that our entire experience of reality may be shaped by perception, belief, and the structure of consciousness itself. Even quantum mechanics hints at this. As we explored earlier, the act of observation affects the outcome of quantum events. Some interpretations suggest that reality does not become definite until measured, raising the possibility that consciousness plays a role in bringing the world into focus. If that is true, then the boundary between observer and observed dissolves. Reality is not something out there waiting to be discovered. It is co-created by the act of looking, thinking, and being. This is not unlike the experience of lucid dreaming, where awareness alters the nature of the dream. In both cases, the perceiver is not separate from the perceived. They are part of the same unfolding process. So, as we sit here tonight, drifting gently between wakefulness and sleep, let us allow ourselves to rest in the mystery of this moment. Take a slow breath. Feel the rhythm of your thoughts, the soft pulse of awareness. Let your mind wander freely, like a traveler walking through the corridors of a vast and endless dream. Ask yourself again, am I dreaming? And if I am, does it matter? Perhaps not, because even dreams can hold meaning. Even illusions can be beautiful. Even simulated lives can be filled with love, joy, sorrow, and wonder. And so, as this segment draws to a close, let us carry this gentle uncertainty with us, not as a burden, but as a gift, a reminder that reality may be stranger and more mysterious than we ever imagined. In the next segment, we will explore a radically different view of the universe, one that suggests particles are not particles at all, but guided by hidden waves of information flowing through space. We will dive into the pilot wave theory, a deterministic alternative to the randomness of quantum mechanics. Until then, let your mind float gently on the surface of this evening's contemplation. Let your Thoughts dissolve like mist in the early morning light and fall softly into the quiet embrace of sleep. The pilot wave theory, a hidden order beneath the chaos there, is something deeply comforting about order, the way stars align in constellations, how seasons follow one another with quiet precision, or how a pendulum swings with rhythmic certainty. Even in chaos, we often search for patterns, for hidden structures that suggest meaning, direction, and control. This longing for order may be what draws us to Louis de Broglie's pilot wave theory, later refined by David Bohm, an interpretation of quantum mechanics that offers a radically different vision of reality than the probabilistic, indeterminate world painted by the Copenhagen interpretation. While many physicists accept that the universe is fundamentally random at its core, pilot wave theory dares to ask, what if everything is actually deterministic? What if there is a hidden order beneath the apparent chaos of the quantum world? Let us begin with the familiar. Imagine watching a marble roll across a smooth table. You can predict where it will go based on its speed, direction, and the forces acting upon it. If you know all the initial conditions, you can determine its future path with absolute certainty. This is classical physics, the world of Newtonian determinism, where every effect follows inevitably from its cause. Now shrink that marble down until it becomes a subatomic particle like an electron or photon. Suddenly, things change. In the quantum realm, particles don't behave like tiny billiard balls, following predictable paths. Instead, they act more like waves of probability, existing in a haze of possible locations and velocities until someone measures them. According to the dominant view, the Copenhagen interpretation, before measurement, a particle doesn't have definite properties. It exists in a superposition of states, represented by a mathematical wave function that gives only the probabilities of where the particle might be found. When a measurement occurs, the wave function collapses into a single outcome, but which one is chosen appears to be random. This randomness has troubled many physicists, including Einstein, who famously said, "God does not play dice with the universe." But while Einstein rejected quantum mechanics outright, others sought alternatives that preserved determinism without abandoning the theory's predictive power. One such alternative is the pilot wave theory, first proposed by Louis de Broglie in the early 20th century and later, expanded by David Bohm in the 1950s. At its heart lies a simple yet profound idea. Particles do have definite positions and trajectories, just like marbles rolling across a table, but they are guided through space by an invisible pilot wave, a kind of quantum field that influences their motion in ways we cannot directly observe. Think of it like this. Imagine a surfer riding a wave in the ocean. The surfer, the particle, has a specific location and momentum, but their movement is shaped by the wave, the pilot wave, which extends across the entire ocean. The surfer isn't randomly appearing here and there. They are moving along a path determined by the wave's shape and behavior. In the same way, according to pilot wave theory, electrons and photons aren't jumping unpredictably from place to place. They are moving along precise paths, guided by a wave that permeates space and time. The wave itself evolves according to the Schrödinger equation, the same mathematical framework used in standard quantum mechanics. But instead of representing mere probabilities, the wave is real, a physical entity that carries information about the system's possible outcomes. This means that, in pilot wave theory, the universe is fully deterministic. There is no fundamental randomness. Every event unfolds as a consequence of prior causes, even if those causes are hidden from our view. The uncertainty we perceive, the fact that we cannot precisely predict where a particle will end up, is not because nature is inherently probabilistic, but because we lack access to the full set of variables that govern its motion. To illustrate this, consider a classic experiment, the double-slit experiment, where particles like electrons are fired at a barrier with two narrow slits. When no one observes which slit the electron passes through, the particles create an interference pattern on a screen behind the barrier, a hallmark of wave behavior. But when detectors are placed at the slits to observe the path of each electron, the interference disappears, and the electrons behave like particles again. The Copenhagen interpretation explains this by saying that the act of observation collapses the wave function, forcing the particle to choose a definite path. But pilot wave theory offers a different explanation. The particle always takes a definite path, but its trajectory is influenced by the pilot wave, which passes through both slits simultaneously. The interference pattern arises not from the particle being in multiple places at once, but from the wave guiding the particle in a way that depends on the entire experimental setup. This subtle distinction changes everything. It suggests that the strange behavior of quantum systems doesn't require abandoning determinism or embracing randomness. Instead, it reveals a deeper layer of reality, one governed by hidden variables and non-local influences. And this brings us to one of the most intriguing features of pilot wave theory, non-locality. In classical physics, objects influence each other only through direct contact or via fields that propagate at finite speeds, such as light. But in pilot wave theory, the pilot wave is non-local, meaning it can instantaneously affect particles regardless of distance. A change in one part of the wave can influence a particle far away, seemingly violating the principle of locality. That underpins relativity. This non-locality is not unique to pilot wave theory. It also appears in quantum entanglement, where measuring one particle instantly affects another, no matter how far apart they are. Einstein called this spooky action at a distance, and while it doesn't allow for faster-than-light communication, it challenges our intuitions about how the universe should work. For some, this non-locality makes pilot wave theory less appealing than the Copenhagen interpretation. After all, if we're going to accept something strange, why not embrace randomness over hidden waves and instantaneous connections? But for others, pilot wave theory feels more satisfying precisely because it restores a sense of order and clarity. Unlike the Copenhagen interpretation, which treats measurement as a special process that collapses the wave function, pilot wave theory applies uniformly to all systems, whether observed or not. There is no need for a privileged role of consciousness or measurement. Reality simply unfolds according to deterministic laws, even if those laws operate beyond our current ability to perceive. This raises a fascinating philosophical question. Is it better to live in a universe that is fundamentally unpredictable, or one where everything is already written, but we simply cannot read it? Some find comfort in determinism, the idea that the universe is not chaotic, that everything happens for a reason, even if that reason remains hidden. Others feel uneasy at the thought that free will might be an illusion, that our choices are merely the unfolding of a script written in advance by unseen variables. Still, pilot wave theory does not necessarily eliminate free will entirely. Even if the universe is deterministic, our subjective experience of making choices remains real. From our limited perspective, the future is unknown, and decisions feel meaningful. Perhaps, in the grand unfolding of events, the illusion of choice is enough as we sit here tonight. Contemplating this hidden order beneath the surface of reality, let us allow ourselves to rest in the quiet mystery of it all. Let your thoughts drift gently, like leaves carried on the wind of awareness. Imagine the pilot wave flowing silently through the fabric of space, guiding every particle, every atom, every breath you take. Imagine the universe not as a game of chance, but as a vast, intricate dance. Each step choreographed by forces we may never fully understand. And yet, within this dance, there is still room for wonder, because even if everything is predetermined, the beauty of discovery remains. Even if the wave is hidden, the surf still rises. And even if the path is known, the journey is still yours to walk. In the next segment, we will explore one of the deepest mysteries of all, free will. We will ask whether our choices are truly ours, or whether they too are shaped by the laws of physics in ways we cannot escape. Until then, let this gentle rhythm carry you further into the embrace of sleep. Let your mind soften like sand shifting beneath the tide, and fall softly into the quiet hum of the hidden order beneath it all. Free will versus determinism. The quantum escape route. There is a moment just before sleep takes you fully, when the mind begins to loosen its grip on certainty. Thoughts drift like clouds across a quiet sky, and questions that feel too heavy in daylight become soft and curious in the hush of night. One such question lingers gently at the edge of awareness. Are my choices truly mine? This is the heart of one of humanity's oldest philosophical dilemmas, free will versus determinism. On one side lies the belief that we are autonomous beings, capable of making decisions independent of external forces. On the other stands the idea that every action, thought, and feeling is the inevitable result of prior causes, stretching back through time, perhaps even to the birth of the universe itself. In a deterministic universe, everything happens because it must. Every decision you've ever made, from what to eat for breakfast to who to love, was set in motion long before you were born, dictated by the laws of physics and the initial conditions of reality. If this is true, then free will may be nothing more than an illusion, a story the brain tells itself to make sense of a world already written. But here, in the strange and shimmering realm of quantum mechanics, there may be a way out. Let us begin with the classical view, the kind of determinism that governed physics before the quantum revolution. In Newtonian mechanics, the universe was seen as a vast machine, ticking forward according to precise mathematical rules. Given enough information about the position and momentum of every particle, it was believed one could predict the future with absolute certainty. This vision of reality left little room for spontaneity or choice. It painted human beings as complex cogs in a cosmic clockwork, moving along paths already carved into the fabric of existence. If everything follows cause and effect without deviation, then what space remains for freedom? Yet most people experience themselves as agents, beings who can choose, who can act, who can shape their own lives. Even if our actions are influenced by genetics, upbringing, and environment, they still feel meaningful. We praise courage, condemn cruelty, celebrate creativity, all under the assumption that individuals are responsible for what they do. So how can we reconcile this deep inner experience of agency with the possibility that everything is determined? 1. Potential escape route appears in the realm of quantum mechanics, a place where randomness seems to rule the microscopic world. According to the standard interpretation of quantum theory, certain events, such as the decay of a radioactive atom, are not predetermined, but occur probably. There is no hidden variable, no deeper law that dictates exactly when the atom will decay. Instead, it simply happens at some point within a range of possibilities. This introduces a crack in the wall of determinism, a place where chance enters the system, and within that crack, some have suggested, might lie the seeds of genuine free will, if the brain operates in part through quantum processes, and some theories suggest it might, then perhaps the indeterminacy of quantum events allows for real choice. Perhaps consciousness does not merely follow the script of physical law, but participates in shaping outcomes in ways that are not entirely predictable. This idea has been explored by thinkers like Roger Penrose, who propose that microtubules within neurons may support quantum effects that contribute to conscious decision-making. If true, this would mean that the mind is not entirely bound by classical determinism, but has access to a level of uncertainty that opens the door to freedom. However, this raises another troubling question. If free will depends on randomness, then is it really free? After all, if your decisions are based on quantum fluctuations, essentially random events occurring at the subatomic level, then you are not truly choosing. You are simply being tossed around by chance, like a leaf in the wind. This suggests that free will, if it exists, cannot be reduced to mere randomness either. What, then, is the alternative? Some philosophers and scientists propose a middle path, a concept sometimes called quantum agency or volitional indeterminism. According to this view, while quantum events introduce an element of unpredictability into the system, they do not eliminate structure entirely. Consciousness may play a role in selecting among possible outcomes, not randomly, but meaningfully. In this model, the brain acts as both a receiver and a shaper of quantum possibilities, allowing for decisions that are neither strictly determined nor purely random. This perspective aligns with our subjective experience of choice. When faced with a decision, we often feel that multiple options are open to us. We weigh them, consider consequences, and eventually settle on one. It doesn't feel arbitrary, and yet it also doesn't feel completely predetermined. There is a sense of participation, of actively shaping the outcome, rather than merely observing it unfold. Still, many critics argue that even if quantum effects influence neural activity, they don't necessarily grant us true autonomy. After all, randomness is not the same as freedom. Choosing between two doors because a coin flip landed heads or tails doesn't make the choice yours. It makes it the result of chance. And yet, perhaps this is too narrow a definition of freedom. Perhaps free will is not about making choices in complete isolation from causality, but about having the capacity to reflect, deliberate, and respond in ways that feel authentic and meaningful, even in a deterministic universe. The complexity of human cognition creates the appearance of choice, and appearances can matter deeply. The illusion of free will may be so richly woven into our mental architecture that it functions indistinguishably from the real thing. From a practical standpoint, we treat each other as moral agents, regardless of whether our actions are ultimately determined. We hold people accountable, celebrate their achievements, and mourn their failures, all under the working assumption that individuals have some degree of control over their lives. But what if that assumption is not just useful, but fundamentally correct? What if the universe, though governed by deep laws, allows for pockets of genuine agency, spaces where consciousness plays an active role in shaping reality? What if the brain, far from being a passive machine, is a dynamic system capable of interacting with quantum-level uncertainty in ways that give rise to meaningful decisions. This brings us back to the observer effect and the role of consciousness in quantum mechanics. As we explored earlier, some interpretations suggest that observation plays a unique role in collapsing wave functions and determining outcomes, while most physicists reject the idea that consciousness is necessary for collapse. The broader question remains: could awareness introduce a subtle form of influence into the unfolding of events? If so, then perhaps free will is not a contradiction within a lawful universe, but a natural consequence of the interplay between determinism and indeterminism, a dance between order and chaos in which we, as conscious beings, take part. Let us return now to the personal dimension of this question. Close your eyes for a moment. Take a slow breath. Let your thoughts settle like dust in a sunlit room. Ask yourself again, am I free? Do you feel the weight of past choices pressing upon you, shaping your present in ways you cannot change? Or do you feel the quiet thrill of possibility, the sense that something new can emerge, that the future is not yet sealed? Perhaps both are true. Perhaps we are shaped by forces beyond our control, biology, culture, history, and yet within those constraints we still find space to choose, to grow, to create meaning. Perhaps free will is not an all-or-nothing proposition, but something more fluid, a spectrum along which we move, depending on context, awareness, and intention. And perhaps, in the end, the question is not whether free will exists in an absolute sense, but whether believing in it helps us live better lives. Because if we believe we are powerless, we may act accordingly, retreating into apathy, resignation, despair. But if we believe we have the capacity to shape our lives, even within limits, we may find courage, purpose, and hope. As we sit here tonight, contemplating this mystery, let us allow ourselves to rest in the quiet space between certainty and doubt. Take another breath. Feel the gentle rhythm of your thoughts, the soft hum of awareness beneath them, and know this: whether your choices are ultimately yours or not, the experience of making them, of loving, learning, and longing is real, and that may be enough. In the final segment of our journey, we will explore one last mystery, the deepest question of all. Are we the observers of reality, or are we part of it? Until then, let this quiet reflection carry you further into the embrace of sleep. Let your mind soften, like ripples fading, into still water, and fall gently into the peaceful unknown. The participatory universe. We are the observers of reality. There is a moment, just before sleep takes you fully, when the boundaries between self and world begin to blur. You lie still, your breath slowing, your thoughts drifting like clouds across a twilight sky, and in that quiet space between waking and dreaming, something profound stirs beneath the surface of awareness. It is not a thought, exactly. It is more like a feeling, a deep, wordless knowing that you are not separate from the universe, but part of it. Not an outsider looking in, but a thread woven into the fabric of existence itself. This is the heart of the idea we now explore. The participatory universe, the suggestion that reality does not exist independently of observation, and that consciousness plays a fundamental role in shaping what is real. Let us begin with a simple question. If a tree falls in a forest and no one is there to hear it, does it make a sound? The answer seems obvious. Yes, of course it does. Sound waves ripple through the air, whether or not someone is present to perceive them. But this assumes that sound is an objective property of the world, that it exists apart from perception. What if this assumption is incomplete? In quantum mechanics, we have seen again and again that the act of measurement changes the outcome of events. A particle behaves differently when observed. A wave function collapses only when someone looks. The double-slit experiment reveals that photons behave as waves or particles, depending on how they are measured. These phenomena suggest that the observer is not merely passive, they are participatory. This idea was most eloquently expressed by physicist John Archibald Wheeler, who proposed that the universe is not a fixed structure waiting to be discovered, but a dynamic process in which observers play an essential role. He famously said, "No elementary phenomenon is a real phenomenon until it is an observed phenomenon." In other words, reality may not be fully real until it is witnessed. This does not mean that the universe only exists. When we look at it, that would imply solipsism, the belief that only the self exists. Rather, it suggests that the universe unfolds through interaction, that information, relationship, and observation are intrinsic to its nature. Imagine the cosmos as a vast ocean of potentiality, a sea of possibilities waiting to become actualized. Every event, every particle, every star is not isolated, but connected through fields of influence and correlation. And somewhere within this ocean swims consciousness, aware, curious, reaching out to touch the unknown. When consciousness observes, it does not simply record what is already there. It participates in bringing it into being. This view resonates with many ancient spiritual traditions, particularly those that speak of the unity of all things. In Buddhism, for example, the concept of sunyata emptiness suggests that nothing has independent existence. Everything arises in dependence upon causes and conditions. In Advaita Vedanta, a school of Indian philosophy, the world is seen as a manifestation of consciousness, not separate from it, but inseparable. Modern physics, in its own way, echoes these insights. At the quantum level, particles do not have definite properties until measured. They exist as probabilities, mathematical descriptions of potential outcomes. Only when an interaction occurs, when information is exchanged, does one possibility emerge as real. This raises a stunning possibility. Perhaps the universe is not a machine running on predetermined laws, but a living system unfolding in response to participation. Perhaps the cosmos is not silent and indifferent, but listening, responding, evolving through the act of being known. Consider the implications. If consciousness helps shape reality, then what we pay attention to matters deeply. Our questions, our curiosity, our choices, they are not external to the universe, but part of its unfolding story. And if that is true, then perhaps the scientific method is not just a tool for understanding the world, it is a sacred act of co-creation. Each experiment, each discovery, each moment of insight is a dialogue between observer and observed, between mind and matter. This leads us to another unsettling thought. If the universe depends on observation, then what existed before conscious beings evolved? Did the Big Bang unfold in a haze of uncertainty, waiting for life to arise so that it could finally become real? Wheeler himself speculated about this, suggesting that the universe might be a kind of self-excited circuit, a system that brings itself into coherence through recursive observation. In this model, the past is not fixed until the present looks back and gives it meaning. Think of it like this. Imagine watching a film reel. Each frame exists independently. The entire story is already there, fully recorded, when you play it. It seems as though characters are making choices, events are unfolding, and time is progressing. But in truth, every moment is fixed, static. Your brain constructs the illusion of movement and change through rapid succession of still images. Could something similar be happening with time and reality? Could the past only become real when the present observes it? This idea is difficult to grasp and even harder to prove, but it invites us to reconsider our place in the cosmos. We often think of ourselves as small beings in a vast universe, tiny specks of dust on a pale blue dot, adrift in an indifferent void. But what if we are not small at all? What if we are not separate from the universe, but its very eyes, its way of seeing, knowing, and becoming? This is not mysticism dressed up as science. It is a philosophical interpretation, rooted in the strange findings of quantum theory. Whether or not consciousness truly shapes reality, the fact remains that we are deeply embedded in a universe that responds to inquiry, that reveals itself through observation, that unfolds through relationship as we sit here tonight. Contemplating this mystery, let us allow ourselves to rest in the quiet wonder of it all. Take a slow breath, feel the rhythm of your thoughts, the gentle pulse of awareness. Let your mind expand gently, like ripples spreading across a still pond. Ask yourself again, am I observing the universe, or am I part of it? And in that question, let go of the need for answers, because sometimes the greatest truths are not found in certainty, but in awe in the end. We may never know whether consciousness creates reality, or whether reality gives rise to consciousness. Perhaps both are true. Perhaps the distinction dissolves in the presence of wonder. But one thing is clear. You are here now, breathing, thinking, feeling, thinking, feeling. And in that, you are participating in the unfolding of something vast, mysterious, and beautiful. So let this final segment carry you further into the embrace of sleep. Let your thoughts soften, like sand shifting beneath the tide. Let your body sink deeper into the mattress, as if returning to the earth from which it came, and fall gently into the peaceful unknown, knowing that wherever you go, you are part of the great unfolding story of the universe. Good night.